Hi, welcome to this webinar brought to you by Cobiax USA. My name is Mike Moda. I'm the Director of Engineering here at Cobiax USA. The goal of this webinar is to show you how to model Cobiax voided slabs in SAFE, a commonly used structural analysis and design program. Although there's an assumption that you have a knowledge of Cobiax voided slabs, I'm going to take a few minutes nevertheless just to go over some of the basic principles. And then towards the end of the webinar, we'll get into how to model Cobiax voided slabs in SAFE. So you see the concept of hollowness even in nature, where the bones of a bird in a wing are hollow. So they're light and yet strong enough for flight. You see the same thing in buildings. As far back as 2,000 years ago, the Pantheon in Rome, where the roof structure was built with these voids to reduce the dead load on the walls. So fast forward 2,000 years, the technology has certainly improved, but the concept remains the same. So how can we then help you with Cobiax voided slabs to address your project? So there's three different ways shown in this graphic that kind of capture the utilization of Cobiax voided slabs. Let's start by looking at the top line where we have two different slabs, a flat plate, solid flat plate, and a Cobiax voided slab on the right of the same span. And so if we compare the two, again, with a similar span, we can see that the weight of the voided slab is decreased by as much as 35% and the thickness by as much as 12%. On the other hand, if you want to compare the same dead weight between the two types of slabs, you can see that the voided slab, the thickness is increased by about 40% and the span increased by about 40%, again keeping the weight the same between the two. However, the most economical use and consideration for voided slabs, Cobiax voided slabs, is where we can remove beams from slabs, from a beam and slab. And so in this case, we're comparing the beam and slab here with a Cobiax voided slab. And as you can see, we can have the same span with a thinner slab. And we remove beams. Beams are expensive to construct. They take up a lot of floor-to-floor height, so we can reduce the floor-to-floor height of the structure, which can have a significant impact on the overall cost of the structure. Also, by reducing the dead load by as much as 1/3, we can reduce the impact on the foundation cost, especially if you're building on piles. So from a design principle standpoint, Cobiax voided slabs are designed much like a conventional flat plate. Okay, you use ACI 318. You start by coming up with the slab thickness using deflection criteria, span to depth ratios in the code. And then you have three modifiers that you have to consider. Obviously, there's a dead load reduction, there's a stiffness reduction, and the shear reduction. And we'll talk about those three in a little bit. But again, you can apply common FE tools. In this case, we're going to look at SAFE. So typically, the slab dead load reduction could be as much as 30% by having voids. The slab stiffness is reduced by 10 to 20%. And this is because you're removing the concrete from the middle half, if you will, of the slab, where it's really not doing anything to carry the load, while keeping the concrete that's doing the work on the top and bottom of the slab. Obviously, by having voids in the slab, there's a reduction in shear capacity that could be as much as 50%, as you can see here. So Cobiax offers two types of voids, the SL line or slim line, as you can see here. And these typically range for slabs, thin slabs from 8 inches up to, you can go to 12, 16 inches. And again, you can download this information, this application data at www.cobiaxusa.com. The other line of voids, Cobiax voids, is called the CLS line. And this is typically used for thicker slabs. Okay, so 16, 18, 20-inch slabs. And again, the application data includes the stiffness reduction factor, the shear reduction factor, the weight reduction, even as much as the CO2 emission reduction, which is an important parameter if you're trying to demonstrate that this is a green, environmentally friendly product. Again, go to cobiaxusa.com to download this CLS PDF. So for the purpose of this webinar, I put together a very simple flat plate that you see here that we're going to model the voids in using SAFE. So the spans in the short direction are 30 feet and in the long direction are 45 feet. Okay? And we're going to use a 16-inch CLS slab. Okay? That's labeled CLS 290 voided slab. And if you look at the table, here you can see that the bending, the stiffness factor, stiffness factor reduction is 0.85, so 15% reduction as compared to a flat plate. The shear is 0.41, and the weight reduction is 67 pounds per square foot load reduction. And again, you go to SAFE, the slab property modifiers, and you input those values as shown here. For the weight reduction, we can go to this section of SAFE, the slab type area object information, where we put in the loads, for example, for live load, in this case is 50 pounds per square foot, or superimpose that load of 20 pounds per square foot. And here we input that load as a negative value of 67 pounds per square foot. Okay, and so this is how you would model the dead load in SAFE. So for this example, for this webinar, I put together a very simple numerical example to show you how to model the Cobiax voids in SAFE. So here we have a slab with 6,000 psi concrete. The two-way shear stress capacity of this slab is given by the ACI code equation. You'll notice that the 31819 code equation has one new factor, which is a size effect factor, lambda sub s, and that lambda sub s is given by this equation, which is less or equal than 1. The bottom line is that if your slabs are thicker than 10 inches, there's a shear penalty associated with this equation. It's a size effect consideration. So if we put in the values, and in this case, phi 0.75 for shear, the value 4, lambda sub s in this case is 0.62. So there is a significant shear penalty here by going to with the 16-inch slab, and square root f prime c. So the two-way shear stress is 144 psi. Now we can have the shear reduction as much as 50%. That would be the most you would have. I'd mentioned 0.41, but in this case, just to keep it simple, I'm using 50%, which results in 72 psi. So using a 16-inch slab, we need to be able to put this information into SAFE in a way that we can look graphically and see where the shear stress exceeds this 72 psi. So the shear load per foot on a 16-inch slab is given by taking the reduced shear stress, multiplying by the slab thickness, and then transforming that into cubes per linear feet. And in this case, it's close to about 14 cubes per linear feet. So you go here into the slab forces and stresses in SAFE, and you select Vmax to look at the shear stresses. And the contour range with a minimum value of 14 and a maximum value of 14.01. Okay, you plug that in, and the program generates this graphic that you see here. So the blue areas are the areas of high shear stresses where the shear stresses have exceeded the 14 cubes per linear feet, or the 72 psi, if you will, around, and this happens around the columns, as you can see here, as well as the exterior columns and corner columns. Okay, And so this is essentially, it's very simple to do, but that's how you would manipulate SAFE to be able to see where the shear stresses are or what they are around the column. So here, for example, you see that as you go right inside of this contour range or contour line, you'll see that the value is 14.3 kips per feet, and that exceeds the 14 kips per foot value that we had determined as the limit. So I put together this slide just to help you from a preliminary design standpoint. How do you estimate how much of the slab should be solid, how much of the slab should be hollow? And so, from a preliminary standpoint, you may consider, for example, and I show here the column strips, okay, in the X direction, if you will, and the column strips in the Y direction. The intersection of the column strips, it would be perhaps an ideal place, if you will, to make the slab solid, and then refine the design as you go through the analysis. And as you can see here, there could be some optimization done by reducing the size of the panel. But at least you have a starting point, which, again, just to reiterate, is the intersection of the column strips in the X and in the Y direction. Okay, and likewise on exterior columns, you'd have the column strip, which is 1/4 of the span in each direction. Okay, so that's essentially it in a nutshell. I hope you enjoy this webinar, and if you have any questions, don't hesitate to reach out to us. We're here to help you with your project. So again, this is how you get a hold of us. My email is mmoda@cobiaxusa.com. So reach out to us, ask questions. We can help you with feasibility studies on your project. If you go to cobiaxusa.com, you can download a lot of good technical information, as well as you're able to see the different types of projects that we have been involved in throughout the United States. So thank you for your time, and I look forward to hearing from you.